I'm just going to go over a few examples of how to solve a series and parallel circuit problems using Ohm's law we've been doing in class. Now our first example is a series circuit, and we have three loads. Now there are a couple of different circumstances you can run into, and the first one we'll do is when we're dealing with identical loads. So in this case, R1 equals R2 equals R3. So for all intents and purposes, you could say the equivalent resistance of the entire circuit is R1 plus R2. What this means is the current coming from the battery is determined by R equivalent, not by the resistance of any one particular load. So if we use Ohm's law, V equals I times R. If in our example we have, say, a 3-volt battery, which is a pretty standard battery, and our resistance is, say, 1 ohm per load, then V is equal to 3 volts, R is equal to 3 ohms. We solve for I, so V equals I times R. To solve for I, we have to divide through by R. Whatever we do to one side, we have to do to the other. The R divided by R equals 1. So now we have I equals V divided by R, which will be equal to 3 volts. And always put the units in, divided by 3 ohms, which is going to be equal to 1. Formula to remember is that the load a handy rule to remember is that the voltage across any load in this case is voltage. So the voltage across any one of these loads is the voltage source, which of course is this, the battery, divided by the number of loads, which in this case is 3 volts, divided by 3, which is 1 volt. And if you were to take your voltmeter, and you always measure voltage in a parallel arrangement, that would equal 1 volt. The situation is more complicated if the loads are not identical. In this case, you have to use Ohm's law individually. So if R1 equals 1 ohm and R2 equals 2 ohms and R3 equals 4 ohms, then the equivalent resistance now becomes 7 ohms. And now the current coming from the circuit becomes V divided by R, which now becomes 3 volts divided by 7 ohms, which is going to be approximately 2 amps. Now, to calculate the voltage drop across each individual load, you have to use this value and each individual resistance. So you have to do it 3 times. So V1 now becomes I times R1, which is going to be 0.42 times 1 ohm, which is going to be 0.42 volts. For parallel circuit arrangement, the situation is somewhat different. When the first case, the loads are identical, determining the equivalent resistance for the entire circuit requires we take the reciprocal. And this just means that in a parallel arrangement, the total resistance of the circuit goes down as you add loads. R equivalent equals 3, and if we want to solve for that, it becomes R equivalent times 1 over R equivalent equals, and then we divide R equivalent equals 1/3 of an ohm, or 0.33. So in this case, the current going through now becomes V equals I times R equivalent. That we solve for I divided by R, which will give us 1 amp in this case. So we have 1 amp of current coming from this circuit. And a nice little rule of thumb is that the current across each load is equal to the source current divided by the number of loads. In this case, that would be 1 amp divided by 3, or again 0.33 amps. When the loads are non-identical, you must do this calculation in order to get the R equivalent, and that equals 0.57, or we'll just round up to 0.6 ohms to make things easy. And so to calculate the current, V equals I, V source, R equivalent, and our source again is 3 volts, equivalent, which is 3 volts divided by 0.6 ohms, which equals, let me get my trusty calculator going, 0.6, 5. Oh, is that ever cool? 5 amps equals the voltage across 1, equals the voltage drop across 2, equals the voltage drop across 3. So what you have to do is 3 separate Ohm's law calculations to determine how that current splits up. So I'll just do one example. You can do the rest. V1 will be I source. And V1 will be I times R1. V1 will be so I1 is 3 amps. And to finish this, you can do the other two.